Okay, so let's recall what we have. So K is always over C. Have already discussed why we are considering here C complex number, right? And Kn, which is just the tuple n tuple, is an element, or to say n tuples of the element from K, and it is known as affine n space. And this one is just the polynomial ring over K. And let me add here this one. The Hilbert basis theorem says that this polynomial ring, which is over K here, is always Mendelian, which means that every ideal in this ring is finitely generated. Right? So by Hilbert basis theorem, every ideal in this ring is finitely generated, which means that whenever you will consider any ideal, you can always find a finite collection of polynomials such that that polynomial collection generate your ideal, your required ideal. Okay, that is the Hilbert basis theorem. Okay, then how we have defined an affine algebraic variety. So affine algebraic variety is nothing just a subset of affine space, which is defined in this way, that is just a zero set of some finite many polynomials. So which means that you can always find a finite set of polynomials which gives you that the zeros of all these polynomials gives you your affine variety. So affine variety is just nothing, just the zero set of your given set of polynomials, right? Okay. Now what we have, this is what we have defined as a variety, which is coming just from the finite collection of polynomials. Then there was a question, if we have any arbitrary set in the polynomial ring, so it may consist of many polynomials other than finite ones, then if you will say that what is this zero set of these all collection of polynomials, then we will just define in a similar way as we have defined the affine variety. And then we can see that this zero set of this set S is nothing just the same as the zero set of the ideal generated by this polynomial S. Because we know that every element in the ideal can be written as a just the combination of the elements from finite combination of the finite combination of the elements from this set S, right? So that's why if you will look the zero set, they are equal. And then what we have defined for a given any set, now we have considered any set in our affine space, we have defined this ideal corresponding to this A, which is nothing just all those polynomials which are zero on these all elements of A. So this polynomial, if I'm considering this polynomial from this ideal of A, this means that will be zero on this A set, right? So whenever you put you plug the values from A in that polynomial, that gives you simply zero. Okay, now we have this property. If A1 is a subset of A2, which is of course in our affine space, then the ideal corresponding ideal with A1 contains the ideal of A2, because you know that from here, when you will consider that if your set is smaller than, then definitely there are more polynomials which satisfy that one. And when you will consider the more, you will extend your set, then definitely you will have some small set than the previous one, the ideal. And then we have seen that we have these two kind of maps, which is like this V, which is coming from the set from this set, the subsets of Kn, and the other one is defined in a different way. From here, we can consider the all ideals which are from their polynomial ring, and we are going back to the affine space. So this gives you some connection here, but we have already seen that this connection is not really like 1, 1 and on 2 map, because these are sort of maps like from one set to another one. but these are actually not inverses to each other. But this is very much true because we already have this one. If you will consider any affine variety, then that affine variety is nothing just equal to the corresponding ideal, and then you will just apply the variety on that ideal, you will get that the same one. But it is not true in general for this one. The ideal of a variety of some ideal I is generally not equal to I. And we have seen an example in the last case where I is just the ideal which is generated by x square. So you can verify by yourself as well now that it is not true for this ideal. So what is true? So this gives us some suggestion, and definitely there is Hilbert-Null-Stellensatz theorem, which is main fundamental theorem in algebraic geometry, which gives you the complete connection between affine varieties and the algebraic part. And it says that it is not actually equal to this ideal, but it's the radical of that ideal. And what is the radical of that ideal? Means that you will select all elements from your ring, bigger ring, such that their powers are in your ideal. That is called the radical of I. So every time you will not get exactly I here, but the radical of I. So this means that if you will just consider all radical ideals, which means that radical ideal means you are considering all ideals which are actually equal to their radical. So that's the definition of radical ideal. So now if I will restrict my sets, here is affine varieties in Kn and here is all radical ideals in this polynomial ring, then definitely what we have the inverses to each other. So we can go from one side to another side and come back to the same one. Okay, so this gives you the sort of complete picture about the geometry and algebra part, right? So we have that one. And now we can talk about the topology on Kn. So here, what kind of topology we are considering at this moment? So if you will look these 2 points, which I have mentioned here, and we have already seen that in the previous lecture, that if you are considering 2 varieties, what about their union? Union is also a variety or not? So answer is yes, union is also a variety. And similarly, the intersection of the varieties is also a variety, which is given by the union of all ideals, which is again an ideal definitely. And if it is not an ideal, then definitely you can consider just the generating set of that one. Okay, so these 2 things suggesting us, what is suggesting us, that finite union of varieties is a fine variety. And if you are considering the intersection, arbitrary intersection is again an affine variety. And empty set and Kn itself, they are affine variety because empty, how we can getting the empty set? Empty set can also be written in this way. What is that? If you will just consider simply one. Again, so we'll just consider a constant polynomial, right? Because if I will consider here a constant polynomial, this actually gives me a whole ring. Ring actually, this whole ring is a polynomial ring, and this gives you just the empty set. So this means that empty set is also an algebraic variety. And similarly, what is Kn? What are the polynomials? Here you can see that what are the polynomials whose are 0 at all points of Kn. Definitely there is only one polynomial which gives you this answer. That is nothing, just the 0 polynomial. So this means that empty set and Kn, they are already the varieties here, right? And including these 2 points, finite union of varieties is variety. Arbitrary intersection of varieties is variety. This suggesting that kind of topology. And this is saying that the closed sets, because these properties which are satisfied by affine varieties, that are also verified by the closed sets in some topology. So we will define our topology, which is known as the Zariski topology on Kn, in this way that closed sets are nothing just the affine varieties. So when I will say that about some topology, like for example an open set, so open set is nothing just the complement of an affine variety. And what is a closed set is just nothing just an affine variety. Okay. And it's not like the usual topology which you are considering that the Euclidean topology on Kn. It's very different from that one. Because this is not Hausdorff, which is saying that if you have two non-empty open sets, their intersection is usually, you can find the open sets such that their intersection is empty in the Euclidean topology, but in this topology, every time you will consider two non-empty two open sets, their intersection is always non-empty. Okay, then we have talked about the irreducibility, which says that if V can be written in this way, where A1 and A2 are just proper closed sets of V, then we will call V is reducible. And when V cannot be written in this way, then definitely it's called irreducible. So we can see this property, our variety is irreducible if and only if the corresponding ideal is prime. Right? And then we have also in the last lecture we ended up there that every affine variety V can be written as finite union of irreducible closed subsets of V that is in this way. And I have already said that this is the corresponding the primary decomposition of the ideal, right? So if you know that how to compute the primary decomposition of ideal, then the corresponding variety can be written in this way. Okay, so far, if there is any question, please let me know. What is I of x? So this I didn't get your question. X squared.
So
I think this you are asking this question, right? So if your I is this one x squared, I mean ideal is generated by x squared, which means that the all polynomials which are coming in so here I'm just considering this is a polynomial in one variable, right? So this is saying that is a principal ideal, which means that it's generated by just a single element. So every element in this one is just a multiple of x squared, right? So these are the elements of this ideal. So I is actually generated by x squared, and you can see that when you will compute the variety of this ideal, what you will get just 0. And when you will again compute the ideal of 0 element, then definitely you will get just the x, the ideal generated by x. And here you don't have ideal generated by x, which is actually x squared, right? So that's the reason. Okay, so now let's move on. What we will discuss in today's lecture is about the maps between these varieties. So now we know that what are varieties. Okay, the intersection of any non-empty open sets in Zariski topology is always non-empty. So this means that the Zariski topology is not Hausdorff. Got it? Okay, that's great. Okay, so now as I said that what we will do in today's lecture, we will see the morphisms between these varieties. So before that one, let me just introduce one more notion which is called the regular functions, right? So let me start with B, which is our affine variety. So a regular function on B is nothing, just a map, which means a function actually from B to K, right? Such that there is a polynomial. Let's call F. In our polynomial ring, right? Such that phi of x is same as f of x. So what is x here? X is nothing, just this one. So let me just write here, x is nothing, just. Okay, so instead of x, let me just write. Because here I have written this one indeterminate, so let me just write a1 the same as f of a1 up to an for all belongs to V. Okay, which means that every regular function is just represented as a function polynomial function. So it's just a polynomial. So you don't care about the rest of the picture. What is outside of V is going on. We don't care about that one. We are just caring about how it is moving in on V. So on V is just nothing, just like a polynomial map, right? Okay. Okay, you may ask here one question that if this polynomial is unique, which define your function? So general answer is no. It might be possible you have two different representations for the same function, right? So here is a remark that yes, that is not true. So this phi is not uniquely determined by f, right? For example, if you have two polynomials, right? They are different polynomials, definitely, but they are saying that this is same. Which means that for all points on V. So this means that if you will look this difference, this is 0 on this on V. Which means that by definition, we have already seen that this difference is nothing just in the ideal of V. So this means that this can be represented uniquely up to this thing, that their difference is in lying in the ideal of V. Right?
The polynomial f is unique, or
sorry?
The polynomial f.
F and G are not unique. They are different.
No, in the definition of.
In the definition, we didn't say anything about that one, that polynomial is unique or not. But you may ask that you have
to there always exist a polynomial.
If there is a polynomial, then that function is called a regular function. That's a definition actually. If there is some function, then definitely it's called a regular function. Yes. Okay. So the regular function on V on some affine variety is a function which is defined from V to K such that there is a polynomial in definitely in n variables such that sorry, okay, I must write here if not such that this is the function if there is a polynomial such that this pi and f are same on V, right? I mean, regular function is like a polynomial function. You can say that. So every time when you think about what is a regular function, you just think there is some polynomial which is just represented as a regular function. Or a regular function is just nothing, a polynomial function. Okay? We will see examples in a moment. Okay, so let me just complete definition. So now I will define this notation, which is actually called the coordinate ring of V. It is depending on V. It's a collection of all regular functions. On V. And it is known as the coordinate ring of V. Right? And what we can do with this one, this has some algebraic structure. So this is actually a K algebra, which means that we can add two regular functions just like we can add polynomials, we can multiply the polynomials, and we can do the scalar multiplication with K elements as well. And it satisfies some algebraic structure which makes this one into a regular function. Okay. So before going to some examples, let's see what we can do with this so far with this definition. And what we can say something more about this one. This is called the coordinate ring of V. Right? So let me just clean that one.
Yeah, I'm asking to move the remark.
Okay, in my remark, I said that this regular function is not uniquely determined by a polynomial, right? Because if you will consider two polynomials, which satisfy that they are giving you the same regular function, which means that they are satisfying on V, they are giving the same answers on V, then definitely their difference on V will be 0 always, which means that the difference is actually in the ideal. So this means that regular function is unique up to this condition. I mean, it's determined by a unique polynomial up to this condition, which we will write here. We can write here this phi 1 is equal to psi if they are two regular functions on V, and they are equal if and only if their corresponding polynomial function satisfies this relation. Suppose that this is coming from F, this is coming from G, then their corresponding F and G satisfy this relation. Right? Okay, so okay, before giving the example, let me just complete this part here, as I said before. So you can see that we have one thing here, which is our polynomial ring. And we have this K algebra as well. This is also a K algebra, and this is also a K algebra. Right? This is the coordinate ring of V or variety, and this is just a polynomial ring. What can you see here? If you will consider just a polynomial here, if I will just take a polynomial, I can see that this polynomial always give me a regular function. If I will restrict that polynomial on B, right? So this means that we have always a map, which is actually a natural map from the polynomial ring to the coordinate ring of B, right? So this means that I will just define in this way. So this here you have polynomial and determinants, but here we are restricting that polynomial over B, where B is our variety. So this means that this gives you actually a regular function, right? So because I said before, every polynomial is giving you a regular function, just restricting that one over B. So if you know little bit more algebra, let's call this map phi. And let me ask this question: what is the kernel of this phi? Can someone answer this question? What is the kernel of this I? I of B. That's the right answer. This is nothing, just the ideal of B. What is it? What does it mean, the kernel? The kernel means that the all polynomials which are going to 0 here, right? Which means that all polynomials which are 0 on B, whenever you want to evaluate those polynomials on the points of B, this gives you just 0 answer. So this means that the kernel of B is nothing, just the ideal of B, which is consisting of all polynomials which are 0 on B, right? So if you know a little bit like group theory, ring theory, module theory, algebra theory, then you know that by first isomorphism theorem, we have this one. Okay, one more thing which you may ask there, I didn't prove one thing that, or I didn't say anything about this map is surjective or not. What do you think? Is it subjective?
Yes.
Is by definition it is actually a subjective, because every function, if you will look again the definition, this phi is always represented by this polynomial, right? So that's why this is a surjection map. So this means that we have by first isomorphism theorem, this K algebra is nothing just isomorphic to this quotient structure. So now you can see that your coordinate ring is nothing, just the quotient structure, which is quotient out by the ideal of your variety. Okay, now let's see some examples. Now it's time to do some examples. And let's start with a very basic and simple example. What is, now my affine variety is Kn itself, right? So no, in the very first example is my variety is Kn. What do you think? What will be the coordinate ring in this case? Can you guess what will be the coordinate ring in this case? Any answers from the online audience? Okay, so what do you need to know that? No, it's not only 0 polynomial. Okay, if you remember very first thing which I had started from, and I had given the connection between K and the polynomial ring. I started, if you remember my last lecture, then I started that what is the connection between the polynomials and the affine space. And I said that for every polynomial, we can define a map. We can say that I said that time just f, which is Kn to K, which is defined in this way, that f is going, so f is defined in this way. If you will pick any element from here and you are just evaluating that point, on this one. And that's it. So this means that every function, every polynomial is giving you a regular function on your Kn. So the answer is very clear. What will be? That one is nothing, just the whole polynomial ring. Right. And now you can see by this definition as well, right? Because if you know that what is your V, if you know that what is the ideal corresponding ideal, and we have already seen that the corresponding ideal is 0. So this means that this is 0. So if you are quotient out this polynomial ring by 0, which means that you are not losing anything, right? So that's why you have this complete polynomial ring here. Okay, that's great. Now let's see some more examples. Now you have V is nothing, just a point. Now can you guess what will be the coordinate ring in that case? It's K of V. It's coordinate ring, not R of V. Okay. It's just nothing, just I can write here K is isomorphic to K. So now what is the justification of that one? You can justify in both ways. Okay, let's see. If you have this in your point, so if you will go back to the definition, here is just a point. So you just want to see that your function is, you need to just find a polynomial that's satisfying on that just a single point. Right? So this means that this is giving you every constant polynomial. Right? And the other reason is that one, if you will look, the B, which is a point, then the corresponding ideal is just a maximal ideal. Right? And you know that when you will quotient out with this integral domain by the maximal ideal, you will get a field which is nothing, just equal to K. Here, in our case, here it's just K. Right? Okay, that's great. Now let's see more examples. And this is example in our tree, right? So what is your variety here? It's just the zero set of x into x minus 1, which means that this is consisting of just 2 points in K, right? And if you have such situation, what will be your coordinate ring in that case? So definitely, because you know that this is your ideal actually. So that's why the coordinate ring is nothing, just K of x over this ideal. And if you know little bit more algebra, this is nothing, just equal to K with the direct sum of x times K. Sorry.
Yeah, it's not a prime ideal, so its ideal will be different from this one.
Yes, that's why I'm written in this way. Because here x is equal to x squared. So this means that every variables whose exponent is 2 or more than 2, they will be disappeared. And definitely your the polynomials are just like of this form a plus bx form.
My question is that the ideal of this variety should be same as this one.
Yes,
This is not a
you
prime
can
ideal.
verify.
This is not a prime ideal.
No, it's not necessarily for the prime ideal, for the radical ideal. Because that is the radical one, that's why it's the same. Right? So this is nothing, just I can write these are 2 copies of K. Right? Okay. So if you have any question, please ask. In the meanwhile, let me just finish this. Okay, let's see one more interesting example, which we have already. uh, So you remember this example from our previous lecture? This is nothing, just the hyper surface, right? And we have proved that one that is irreducible hypersurface. I know you can answer through this part as well. When I is prime, then it is irreducible. But we have shown in a different way. Okay, so now my question is, what is your coordinate ring in this case? Which of course is nothing just equal to this one. Any answer?
P of X
Linear
direct.
combination of.
Is that?
Linear combination of x, y, and.
Yes.
I think it will be just the sum of
If you remember from the previous example, then you can guess what will be the polynomial in this case.
I think it will be sum of kx
Yes.
and ky. It's just
Okay,
polynomial
so
on
this
x
means
plus
that I
polynomial.
can write this thing in this way. Actually, x inverse. I mean, these are called the Laurent polynomials. So this is the ring of the Laurent polynomials. Because every element in this setup can be written in this way, because I have replaced y by 1
1 over X.
over x. So that's why you are getting the not only the polynomial, but they are the polynomial with the negative exponents. So that's why we can write these polynomial in this way, which are called the Laurent polynomials. Right?
But we can replace,
Sorry?
we can replace, one by the product of x and y. Then it can be viewed as, that sum of k and k of x and k of y.
No,
Mhm.
because we have their multiplication as well.
Mhm.
X, y, when they are multiplying, that's definitely replaced by 1, but that is just x into 1 over x. It's the same thing. So I can write in this way actually. Okay. So I can answer this question in this way, that V is irreducible in terms of coordinate ring if and only if this corresponding coordinate ring is what? Because we know that the corresponding ideal is prime ideal, and definitely if it is a prime ideal, then we know that this quotient one is integral domain. Integral domain means that there is no zero divisor, right? Okay, now it's time to define a map between two varieties. What does it mean, that one? Right? So let's take two varieties. One is from Km, the other one is from Km, from two different n spaces, right? Definitely this might be possible. And now who will be affine varieties? And now we will define a map which is called regular map between these two varieties from V to W. It's nothing, just a function. So you can see that I am just like extending this map, which I have already defined a regular function from on V. So this is a function such that there are polynomials. So let's call them f1 up to xn. Of course, these are polynomials in. Here are m variables, right? Such that this phi of A must be equal to this f1 of A up to fn of A for all A, which is actually equal to this n tuple in V. Okay. So if you look carefully, this is nothing just the extension of that one, because here, if you will go back to this definition of the regular function from V to K, you just need one coordinate there, right? To define it, so you just need one polynomial. But now here we want to define this map from V to W. So which means that your answer must lie in your W. The image must be in your W. So what we have here, this is just a function such that there are polynomials. So we are defining again a regular map through polynomials, which satisfy this relation that if you want to evaluate this phi function on this V, then the corresponding answers on evaluated on these Fi's must be in your sorry, sorry, let me just, okay, this is n, right, this is n. So this one is in W. So be careful with the indices n and m. So I started B's in Km. So this means that B's have m coordinates and W, because W is in Kn. So this means that these we need just n polynomials to define each coordinate. For each coordinate, we need to go to have every time a polynomial. Right? Okay. Like we have seen some examples. For example, if you have let me just write what is our V. Okay, let me just go in the new model to say something about the example. Okay, is there any question related to this new definition, regular map from V to W? Okay, so let's see again this definition. So our regular map is nothing just given by a collection of polynomials. So it's depending on the coordinates, in which coordinates you are picking your variety. So you need to know that your variety W is lined in Kn. So this means that you need n coordinates. So you need n polynomials to define this map. And it just satisfies that one. If this function is satisfying this condition that on each B, it has the evaluated on these polynomials, it gives you answer in W. Right? Okay. So one remark is here that if any regular function which we have already defined on V is actually a regular map from B to A. Agree?
Yeah.
Right? Okay, now let's remark about this regular map again. So if you need to know that if you want to define a regular map from B to W, then what you need to know that? You need to collect a list of polynomials which satisfy certain conditions, right? So if you have that collection of polynomials, how you will say that this is defining a regular map from B to W or not? So for example, if you will pick set of polynomials, let's call it F1 up to Fm, sorry, N, I'm sorry, N is this polynomial ring with M coordinates, then how you will say that this defines a regular map from V to W? How you will say that? What you need to check that one? First of all, we need to see that these polynomials are actually regular functions on V, which means that if I will restrict these one on V, these are nothing just are regular functions on V. Agree? Because we know that corresponding to each one we have such a setup. And furthermore, it satisfies this condition that if you just consider a polynomial in the ideal of W, then it satisfies this thing that if you will evaluate those polynomials on this one, that gives you 0, but all G belongs to the ideal of W. So that is the criterion, you can say that, and that is just coming from the definition of the regular map, that if you have some collection of polynomials and you want to see that these define a regular map from V to W, you just need to see that these are actually regular functions on V. Each actually polynomial defines a regular function on V, such that it satisfies one more condition, that when you have evaluated these one on V, and you just plug in these answers in any polynomial in the ideal of W, it gives you 0. Right? It satisfies this condition. Then you will get your answer that is actually a regular map or not. It defines a regular map or not. Okay? So very simple example. So if you have which is just a projection. I'm assuming here n is bigger than or equal to n. So you have this projection map, and this is actually a regular one. Right? And why you can say that this is a regular map? Because here you will just look these coordinates. These are just polynomials. These are just simple polynomials, but still they are polynomials. It's very, very trivial map, you can say that, but still this is a regular map. Okay, one more example. For example, you have this one in K2, this variety, and now I can define a map from, I can also say that this one is defined in this way. Right? This variety is defined in this way as well. So now I can just define a map from K to V. From T is going to this one, T and P sphere. So you can easily see that this is again a regular map, because in each coordinate you can see that these are just polynomials are appearing here. Right? And similarly, you can see that we can also have this map, which is nothing just the projection. If you have here x, y, this satisfies this condition here. Definitely, I'm picking the element from here, and I'm just projecting this point to the first coordinate. I get this one, right? And furthermore, if I will let's call it phi and let's call it psi. And if you will compose these two maps, you can see that this gives you identity, which means that they are inverses to each other. And both are regular maps. Right? So if you have such kind of situation, then what you will say that? Like in your usual algebraic theory. If you have one map which satisfies morphism types condition, here we have this regular map, and you have also the inverse of that map which satisfies the same condition, then you will say that these are inverses each other, which means that they are isomorphic. Right? So in this way, I can say that this variety is nothing just isomorphic to the affine line. Right? Okay, so I will definitely extend this definition. So let me just add that definition here. A regular map phi from V to W is an isomorphism if there is a map psi from W to A, which is again a regular map. It is important here. If it is not regular, then definitely it's not an isomorphism. Such that it satisfies this condition. If you compose this one, you will get identity on W. And if you will compose in another way down, then definitely I get the identity on V. Right? Okay, is there any question? Okay, if you have any question, please let me know. Okay, now one more thing you can see that what kind of map this is. I will see these maps in terms of the topology. If I'm considering the topology on Kn, which is the Zariski topology, and definitely what I can say about this map, it satisfies a similar kind of condition which we will usually use for the continuity. So answer is yes, every regular map is actually continuous, but this regular map is something more than that one. But definitely yes, the answer is yes. Every regular map is continuous as well. With respect to the Zariski topology. And then what is the reason here? Okay, so for example,
Being a polynomial function.
yes, being the polynomial, and polynomials are actually not really in that way, but okay, let me just complete that argument. So if you have this one, and you know that if I will pick any closed set, because I want to prove the continuity, so I will pick any closed set here, which means that it's just definitely defined by some polynomials, because it is a closed one. So this means that A is defined as right in W. And now we want to see the pre-image of that one. So what will be the pre-image of this one? So you can verify by yourself as well because it's a simple calculation. You can verify that this is nothing just the zeros of
Hello.
these functions. F1
Hello.
5, yes, this one. So that is the reason because this is close here, the pre-image is also close, that's why it is continuous, not through that point. And why we are getting this one, you can easily see here, whenever you have a map, you have a polynomial here, which is going from here to here. You can always define a polynomial, which is coming from V to K, just taking the composition. Right? Okay, this is the reason that this is a continuous map. But of course, it's more than that. It's not just a continuous map. What is the answer?
Can you please repeat the definition?
Which definition?
Regular,
Regular function or regular map?
what regular mapping?
I guess it was isomorphism.
Okay, regular map. So regular map, as I said, that regular map definition is totally depending on how you have defined the regular function. Okay, so so just consider how we have defined this regular map. We will say that this is just a function from V to W, which satisfies this condition that if you can find the polynomials such that if you want to evaluate on this point those polynomials, this gives you the answer in W. Right? Because you want, whenever you say that some function is coming from one space to one variety to another variety, then definitely answer must be, the image of this point must be in W. This means that these valuation point must belong to W. And as I have described here on this board, how you will check that the given polynomials define a regular map from V to W or not. First thing you can notice that when you will just consider single polynomial in each one triple coordinate, that is giving you just a regular function. And furthermore, when you evaluate those polynomials on V, right, and then you want to see, and then you want to apply that answers on some polynomial which is coming from the ideal, this gives you nothing, just a 0, 1. Right? As we have seen in this example. So I have defined here a map from K to V. So this means that I need here 2 coordinates, not just 1 coordinate. Right? So if I will define in this way, so T is going from here, and I need to define 2 definitely coordinates. Furthermore, it must satisfy that this corresponding point must be lying in V. So you can see that I have not defined this one in arbitrary way. I have defined in such a way that the corresponding or the image of that one is lying in your variety. Right? So that's why you are in the first coordinate, you have defined just a t, which is just a polynomial, and then you have just defined the t squared, which is another polynomial in the second coordinate. Right? And this is another way, which is just a projection, which I have already described here. Is it clear to your Fatma? Okay, that's great.
Yes, ma'am. Thank you.
Is there any other question related to this definition?
Ma'am, Assalamu alaikum.
Didi.
Hello,
Didi.
am I audible to you?
Yes, you are.
Ma'am, my question is that please kindly give us the examples of regular map. Please clear it with help of examples.
Okay. Okay. Okay, so let me give you very general definition, I mean general example how you will describe your okay. Let's see that here V is in Km. So when you are saying that you need to define a map from V to Km, so this means that you have here M coordinate, right? And you want to have here some coordinates which are M, sorry, N, right? This is general thing which is we will say that we want to have some function. But now we want to say that this is a regular map, which means that we will every time I will pick this point from here from V and know how my BI's are defined. These are nothing just actually BI's are nothing just coming from some polynomial which are evaluated on these points. So what is BI? BI is nothing, just Fi polynomial, some polynomial, and I have evaluated that one on these points. That is the simple answer. So for example, I'm not taking here what is my variety at this moment. I'm just considering that one in a general way. So let me write here something. So let's say this is lying in K3. So I have three coordinates X, Y, Z. So what I need to put here, just some polynomials.
Ma'am, sorry for interruption.
G, yes, please.
मैम आपका बोर्ड विजिबल नहीं हो रहा स्क्रीन पर काइंडली उसको विजिबल करें
Okay. I think might be you have some internet problem. तभी वो blur सा हो जाता है.
नहीं बिल्कुल उसकी स्क्रीन आ रही नहीं है जिस तरह पहले व्हाइट बोर्ड ब्लैक बोर्ड नजर आ रहा था उस तरह भी नहीं आ रहा मेरे पास.
Okay, if you will see the chat box, some people are saying that it is visible, so it might be problem at your internet problem at your end. So kindly उसको अगर आप थोड़ा सा ठीक कर ले तो.
Or maybe he's not
Yes,
seeing the
ठीक है,
bigger
ma'am,
one. So just click on the three dots and choose the pin screen, then it will be bigger.
Okay, thank you. Thank you so much for your suggestion. Okay. So now you can see that this is another map, which is actually a regular map. But if you have here some other variety, right? So if you have here some other variety, this means that these points must lie in your this variety. So now let me just generalize this one. If you have any questions so far with this definition, please let me know. I think it's very simple to describe here because I already said that if you have point here in your the target space, so what we want here in the target space is that one is written in this way where Fi's are some polynomials like in this example. But if you have some general thing here, D and any other variety, two different varieties, right? So this means that this point, so I'm choosing here, this is in Km and this is in Kn. So this means that, agree? But if I'm saying that this is mapped from V to W, then this point must lie in your W. Agree? So that's why you need here these polynomials which satisfy this condition that the answers which are evaluated those polynomials, they must lie in your W. That is the extra condition when you are considering here W, and that is it. Like here in this example. So as I said that before, that was the example. Let me just rewrite that example. My variety is this one. So you want here some variety. So this means that you can take here any coordinates, but you cannot put here any polynomial actually. I need to put those polynomial when they are evaluated at t. This gives you answer in v. So that's why I will put just here t and t squared, because this is in your v. So that's why this is a regular function from a to b, right? Okay. I hope so. I have explained, try to explain in a very simple manner. If still there is a question, then I will answer those questions at the end of the lecture. Okay, now let me proceed. Okay, so let me go with this another example. So my variety is at this moment is this one. Okay, so we can easily see that we have a map, regular map actually from K to W, which is defined in this way. T is going to T squared and T cubed. Let's see, it's fine, these are polynomial, but we need to see that it satisfies this condition or not. So this is your x coordinate, this is your y coordinate. So if you will take the x coordinate cube and you will take the y coordinate square, you can see that this is also t power 6, this is also t power 6, which satisfy this condition. So this is actually a regular map from B to W, oh, sorry, K to W. Okay. Now, one more thing you can notice that we have also a map from here to here, which is a projection, as we have seen in this previous example. Because we have already said that this is actually an example, a variety which is isomorphic to K. Let's see it's both here or not. So we have from W to K, and from W, I will just pick two definitely coordinates which satisfy this condition, and I'm just projecting that one in the first coordinate. So you know you can see that they are inverses to each other.
No.
Huh? Yes or no? These are actually a bijection.
Yes, yes.
Agree? But this is not an isomorphism. Bijection maps, if you just see the maps, bijection means that 1, 1 and 1, 2 map, no other regularities is there. Right? So you should just look map through. It's 1, 1 and 1, 2, which means that they are just coming in that way. But this is not isomorphism. One, let's answer this question. Right? Okay, so to answer this question, let me just read.
We are talking about the bijectivity of the first map.
Yes, first map. This is just a projection.
Yeah.
It is not of this map. I mean, they are not inverses to each other. But this map, you can say that this is bijection. I mean, when I'm saying that bijection, it doesn't mean that regularity must satisfy. When I'm saying that the isomorphism, so then it means that that is bijection plus the inverse map satisfy the regularity condition. Okay, like you do in the topological space, right? So one map is continuous, and the inverse map must also satisfy that condition, the continuity condition. Okay. So let's see. Let's suppose that, let's call it phi, right, at this moment. Let's suppose that this is an isomorphism, which means that there is another map which is going from W to K, which is again a morphism for us, right? Like regular map.
Ma'am,
Yes,
or if this is not the inverse map, can we define it in another way?
yes. Might be possible. This is not I mean, it's not the inverse one, but there is some other one which makes the inverse of that one. Right? It might be possible. So let's check that one. So let's take psi, which is going from W to K, right? And suppose that this is regular. So this is regular map, which is actually a regular function because we are going from W to K, which is just giving you a regular function on W. So this means that you will get a polynomial, which defines actually your psi, right? So this means that there is some function, let's call it okay, let me just call that one psi of some point, the same as so there is f, which is a polynomial, which satisfies this condition. For all. Okay. So as I said that this, because this is an, I'm supposing that this is an isomorphism and this is this inverse, right? So this means that they must satisfy this condition, which is this one. So phi composed with psi, so this means that it will be evaluated at k elements. So when we will do this thing, this is giving you this one. And when you will apply the psi, this gives you this one. Agree? And when you will have some polynomial here, then definitely it will be applied on some polynomial. And what you will get just the f t please here. So this is just a polynomial at this moment, right? Because the answer is in k, so just evaluate it on these points. So what you can see in this setup? This is nothing, just a polynomial, right? So if you will see carefully this one, so you can see that this polynomial can have a constant term, right? Can have the t square terms, can have t square terms, but cannot have t terms, right? So this polynomial cannot have t, just a t term here. Like when you will write a polynomial in one variable, there is always appearing some coefficient of t, and that is 0 here in that case. So this means that whatever this polynomial is, we know that this does not have a t term here, which means that this thing cannot be equal to t. If I'm saying that this is an inverse of that map, then it must satisfy this condition. But we know that from this calculation, we can see that this can never be t and at any cost. So that's why this will never be t. So this phi cannot be an isomorphism. Okay, what are t squared and t cubed? T is here just an element which is coming from, you can see that from k, because I'm applying phi here first, phi is here. So t is just a variable. T is just a variable. Right? And t squared and t cubed, they are just polynomials in terms of t. Indeterminate जो है, that is t. So that's why these are just polynomials in indeterminate t. Okay. So we have seen that this is not an isomorphism, and now we will see another way to prove that example. Just give me a few minutes. Okay. So whenever you are given a regular map, right? Whenever you are given a regular map, and if you have a map or a regular function, which we call a regular function, from W to K, we can always extend that map from B to K, just taking the composition. So this means that if I'm taking this F from my coordinate ring, and this gives you another function through this map, and this one is a coordinate in the coordinate ring of B. So this means that this map gives you another map which we will call the X-type. It's starting from the K of W to K of B, which are the coordinate rings of the corresponding varieties, and defined in this way, just a composition. And this is called the pullback of phi. So every time whenever you have a regular map, this gives you another map between their corresponding coordinate rings, right? And furthermore, if this map, because this one is it is on the coordinate ring which is K algebra, so definitely it satisfies the definition of the K algebra morphism. And whenever this is an isomorphism here, which means that there is an inverse which is also a regular map, then definitely there will be a map which is also the inverse of this map. So this means that we have this nice result. This says that if phi is an isomorphism, if and only if their corresponding coordinate rings are also isomorphic to this dual pullback, and these are scale data. Right? So if you will go back to this example, sorry, not this example, where is that one? I think I had removed that example, the hyperbola example. If you remember that one, no, this one is not, that one is not here at this moment. Okay, let me just write that
Yes,
down so that you can easily see that. This one. Right? And we have already seen that what is the coordinate ring of this hyperbola? Is nothing, just this the ring of polynomial of Laurent polynomials, right? And if you remember last time we asked such kind of question, we can define a map again with the from H to K, right? So you might ask this question: this hyperbola is isomorphic to K or not? So answer is no, because we know that this one is nothing just equal to this one. So because these two are not isomorphic, so that's why these cannot be isomorphic. Right? Because of this result. Isomorphism. Okay, any questions so far? Okay. sorry, I have removed that example, which I think I made that one. So let me just write it again, which we have already here. Okay, now what we will do, I will just consider my variety, which is irreducible. There is some reason to consider that variety. Now, from now onward, I will just consider that my variety is always irreducible, right? So whenever you have an irreducible variety, so you know that they're corresponding. So V is irreducible. And we know that this corresponding coordinate ring is an integral domain. So whenever you have it, yes. K of H is, I didn't say K of H is actually K of X. This is the same question which you have already asked, and I said that this is actually equal to isomorphic to this one. Not what you have written, and this is K, which is the fine space or a fine line, which is K of X. And I said that because they are not isomorphic, that's why this hyperplane is not isomorphic to this K one line. Right? Okay, this means that integral domain. Which does not have any zero divisor. Right? Okay. So whenever you have an integral domain means that as just before it does not have any zero divisor, then you can extend this integral domain to a field, which is usually we call the field of fraction. Right? So whenever you have this integral domain, because we are considering V is irreducible, so we have this one, which is known as the field of fraction. And it is consisting of what? There we know that they are sort of polynomials. Here will be rational functions, which are just the polynomial over polynomial, right? Which are in K of V, and definitely G is non-zero polynomial, right? This is the same idea which you do in general for the Z, because Z, the set of integer, is a field, is the integral domain, right? And you want to extend into the field which gives you rational numbers, right? And this is the same as you write the fractions, like 2, 1 by 2, 3, 1 by 3. You are considering all those elements in this K of V, right? And definitely they satisfy some certain condition, like you said that 1 by 2 is same as 2 by 4, right? So this means that we have this equivalence relation on those ones. So if you have these two fractions, they are same if and only if they satisfy this condition, right? No, every integral domain is not field, but we can always extend that integral domain to make a field, right? Which means that every non-zero element can have the inverse of it. Like C, set of integer, that is not a field, but that is an integral domain, right? And we can extend that one and we can make this one into a field, like this, the field of rational numbers. That is the whole idea, which is we are extending here from the integral domain, with whatever the integral domain is, doesn't matter. But the idea is very similar and exactly the same idea which you are having for the rational number. What is a rational number? It's just a ratio, just a fraction. So same here, right? And that's why we will call these elements as rational functions on V. So the elements of K of V are called rational functions on V. Which means that what is a rational function? It's nothing, just a usual function which is described in the ratio, in the fraction. You will get two polynomials such that that function can be written as f over g. That's it. Okay, thank you. Okay, so you know that whenever you are writing a fraction, you always said that the in the denominator number is always non-zero, right? But whenever you are considering a polynomial, we are also saying the same thing. G is non-zero polynomial. But it happens sometimes, for example, if you have this variety, let's suppose this is just a map. P is going to 1 over D. Right? So P goes to 1 over 2. So this is a rational map. But you can say that this is not defined at T when T is 0. But still we can consider this is a map, but it is not defined. So I cannot write here this is a map from K to K. I need to write that this is defined on K minus 0 to K. But this is still a rational function on K. I can say that one. So there are some points which are making these kind of things, and we will call such points which are very good. They are called regular one or a smooth points, and otherwise which does not satisfy those conditions, they are called singular points. So let me just extend that definition. So the set of a rational function phi in your corresponding variety is regular at some point x in V if there are regular functions f and g such that phi can be written as f over g, and g at that particular point is non-zero. Right? So here you can say that I can take another point. I can make another rational function which is 1 over t minus 1. This is again a rational function, but definitely at this moment this is not defined at t is equal to 1. Right? So if I will look this one, what are the regular points? I can say that which is k minus 0. But for this one, I can say that that's just k minus 1. I'm just removing these points which are disturbing my function. Right? So this set of all collection, which we call the regular points, right? These collection define the set of points at which phi is regular is called the domain of your function phi. So I will set my domain is depending on those points where my function is regular, or those points are also called the smooth points or the regular points as well, right? So this means that whenever I will consider this one, so that's why I will use this kind of notation. So this is not a map from K to K, it's not indeed a map, but if it is defined in this way, so I will say that this is a rational map from K to K, which is defined in this way, and if I will call this phi, then the domain of this phi is nothing just K minus 0. Right? And if I have this map, then definitely my domain will be different. It is K minus 1 point. Right? So regular points, this X is called a regular one. So where your function is regular, those points are called regular points. I didn't mention that one, but I have just said this thing. Okay, so let's okay, now the question is that can we find always this domain? Domain can be empty or not for the corresponding sum function. So answer is no. Domain is always non-empty open set with respect to the Zariski topology, right? So now we have this result which says that the domain of a rational function phi is a non-empty Zariski open subset of V. Right? Okay, let's see why. So let's consider all f and g which defines our function phi. Because as I said before that we can have two different representations, right? But they are defining the same function. So I have considered all f over g. It's like same like you say that in case of the rational numbers, 2 is same as 4 by 2 or same as 6 by 3 is same as 8 by 4 and so on. Right? So that's why we have collected all those rational fractions in this part. Okay, the set of points at which phi is regular is the intersection of all closed sets which are actually these one. So x belongs to V such that g of x is non-zero. Right? Agree? Because I'm considering here all possible fractions of those numbers. And definitely, then I'm taking what are my points which are regular on, or I will say the set of all points for which the function is regular, that is the intersection of all these closed sets. And you can see that by definition, it is an open Zariski set and it is non-empty definition. Okay, so what is your question? I have answered those questions. What are regular points? I said that on those points on which your function is regular, they are called regular points. Right? I don't know where I have written the capital K. I never use so far.
Just ask. We have another question. Yeah.
And there's another question.
Sorry?
Okay. Are you taking a fact?
Okay, as I said before, I'm just taking the K as a field of complex numbers. Yes. I mentioned at the beginning, I'm not using any other field at this moment, just this, the field of complex numbers. Okay, another interesting point, you can see that if your domain of this rational function is whole V, it is nothing just a regular function on V. If your domain is whole V, then definitely you can just see that that is nothing just the same as a regular function on V. Right? So that is another result which I'm not going to prove at this moment. So if you have this rational function, whose domain is V, then phi is nothing, just a regular function on V. I mean, it's just a polynomial, because you will never find any points which are not good one or not regular, then definitely it's just given by the polynomial. Okay.
So
Yes.
just we come back to field of fraction. Maybe G, it must be
Yes.
different from zero only on V.
Only on?
On V. Should
Mhm.
precise that it is
Here?
different from zero on V, yes.
Yes.
It's not on me.
G restricted to V is not on zero, so which means that G is not in the ideal of V.
Yes, when I'm saying
Yeah.
that F and G are here,
Ah, okay, sorry, yes.
so
yes.
that's why
Yes,
I'm
yes.
saying that
Yes,
G
sorry,
is
yes.
non-zero.
Yes, yes.
Okay? Because I have put that condition
Yeah, yeah.
already
Yes, yes.
there. I asked why you map K to K and if its set of domain is the same as the range. I didn't say that. I have just a map which is defined in this way. T is going to 1 over T, and definitely you can see that its domain is not whole K, is K minus 0.
Domain and range will be same or not?
Okay, domain and range can be same. I mean, it's more important how you are defining your map. Okay, what is domain and what is range? That is very what you are calling the domain. I'm calling the domain of my function is that one where the points, all those points where my function is regular. That is, I'm saying my domain. Right? Domain of, you can say the domain of definition of this function. Where is phi? Yes, here. So this is something which is different domain, and I'm talking here particularly this kind of domain. Domain of phi being that domain of definition of phi. So let me just add here one more point so that you will not confuse with the usual domain, but it is called domain of definition of phi. Okay, I hope so it's answered the question. Okay, now we have the similar kind of construction again. We have a sorry, Okay, so far we have defined the rational functions on V. Now I'm going to extend that idea. A rational functions from V to V, another variety, right? So again, as I said that in this section, I'm just considering the irreducible polynomial. So whenever I'm picking two varieties, definitely both are irreducible, right? So this is in Kn, this is in Kn, and both are irreducible. Okay. So now I will define a rational map. If you really understand what is the regular function and corresponding rational function, and if you know that what was the definition of regular map, and then here we have the rational map, which is coming from the rational functions. The definition is same, just we are switching from polynomial to rational function here. So a rational map so I'm not putting, you can see that this is dotted line, which is clearly say that this is not indeed a map from V to W. I mean, it's not defined on whole V, as we have seen here, right? So this is nothing, just an n-tuple of rational functions phi 1 up to phi n, such that, of course, these are in our field of fraction of on V, right? Rational functions on V, such that for every point in V, this satisfies where actually I need to also consider where these are defined. Because this is important. If they are not defined, we cannot do any calculation. Such that for X, where this is defined, then the corresponding element, I mean this tuple, must be a part of W. So you can see that we just have extended our regular map to a rational map, where we have just considered, instead of rational function, we considered regular maps there. So I'm just considering here rational function will satisfy this condition. Definitely, I need to check on all points on V, but definitely there is no, this whole domain is not working. So definitely we will pick only those points where these functions are defined. So that's why we can see that the corresponding image point is also in the W or not, right? So this defines the rational map. And of course, if where this is defined, this is called the domain of definition of this function. Again, it's the same definition just for this rational map, which is nothing, just the intersection of all domains which are defined for the phi 1 up to phi n. Yes? Okay, any question? Okay, so we have okay, so let me conclude today's lecture with an example. And then I will take more questions from the audience and we'll try to answer those questions. Okay, so I'm taking here H be a hyperplane. Hyperplane means that, and how it is defined, if I will consider just like like a vector space. If you are working in a vector space, so what is a hyperplane? Hyperplane is just a four-dimensional one, right? So here I'm picking this hyperplane, which is defined in this way. I mean, I'm just precisely what hyperplane I'm choosing at this moment. Right? So this is my hyperplane. Okay. And now let's pick this point P, which is the origin. And let's take another hyperplane which is parallel to my given hyperplane and which is passing through this one. This is called HP. Right? So you can see that P is here. When all these are zeros, definitely it's here, but it's not lying here. Definitely we have chosen this P, which is not lying on the given hyperplane, right? Okay, now if you will consider all those points, let X belongs to this Kn, which is not in HP, right? So now we have 2 points. One point is P and other point or any chosen point X. Now just consider a line which is passing through this X and P. Definitely it's a unique line which is passing through X and P, and definitely that line cuts your hyperplane at one point, right? HP is another space. You can say that is another space, right? It's just a hyperplane. It is also called a hyperplane. But it's not a vector space. Sorry, this is not a vector space, but this is actually a vector space. So hyperplane needs not to be a vector space. It can be just like you have a plane. In plane, a hyperplane means that all lines. Okay, so if you are picking a point here, so let me just try to draw that one. So this is your region. So this is my HP. This is my point P, and this is your H. Because these are parallel, so I am picking any point you can pick in your space here. So you are just picking a point here. This is my X. So you are taking a line which is passing through this point X and P, and definitely this line will intersect. Will pass through this H. I mean, this will intersect at some point here. So I will consider my map in this way, right? So I'm defining my map in this way. So phi is a map, right? Which is defined in this way, x1 up to xn is equal to x1 over xn. So you can ask this question that how you will get these coordinates. Definitely there are the equation of the line is involved and then you will take the intersection with H. So that's why you will get this point. Okay. So here you can see that this phi is not defined on whole Kn. What is the domain of this phi in this case?
Kn minus HP. Kn minus HP.
Is
Domain of phi is Kn minus HP.
Kn minus HP. Yes, that's true. Right? So this is one of the example, and it shows that this is a rational function, right? And its domain is not whole Kn, but the Kn minus HP. And let's see another example. Okay, let me just conclude with that example, which I have written earlier. X, y squared is x cube, right? And if you remember, we have this. Actually, this is a regular one, so that's why I can write in this way. You remember this one? P squared Right? So I can define this map in this way, xy, which is going to y over x. And here you can notice that these two maps are bijections, and one of them is regular, but the other one is not regular because it is not defined when x is equal to 0. Right? So this is a rational map. The other one is also rational because every regular one is rational, but the converse is not true. So in this way, we can define this, if it satisfies this inverse property, if one is rational, the inverse is also rational, then we will call this not an isomorphism, but the sorry. But we will call in this way that phi is birational. Birationally equivalent. And your V, W, and this K are birational equivalent. Definitely, it is different from the regularity, that is an isomorphism, but this is birational one. And one more thing, I will just conclude that one. If phi is a map from V to W, and it is birationally equivalent, if and only if the corresponding pullback on the rational maps is an isomorphism of K algebra, of field, sorry. Because in this case, these are fields. Right? So this concludes the whole theory at this moment. If you have birational, then the corresponding field of fractions, they are isomorphic. And this is also if and only if one. Right? And you can see this example here. So W is not isomorphic to K, but it is birational to K. Okay, so now you have any question, please ask me.
What you wrote in the last line?
Is isomorphism of field as a field, because here the isomorphism is depending what are the algebraic structure they have. So please, if you have any question.
Sorry. For this,
Okay,
for this isomorphism of field,
yes,
if we restrict it to
Very-
if we restrict it to the coordinate range.
it's not because it's not depending the coordinate ring.
Yes.
So they're corresponding field of fractions,
Yes.
because no, they are field, so that's why the isomorphism is as a field.
Yes, it
Isomorphism.
is an isomorphism of field.
Yes.
And this field, we obtain this field as the field of fraction of our coordinate ring.
Yes,
And if we have this isomorphism, it will be the identity on our integral domain, no?
yes. Yes,
So-
I can say that this information is not complete. If you will restrict that one on the integral domain part, I mean on the coordinate ring, then definitely that is like the what we call, that's just like a isomorphism as an integral domain.
But yes, this is the point. We have said that birational is weaker than
Yes,
than
isomorphism.
But here we are saying
Yes,
that it is
I agree.
isomorphism of field. So we can restrict ourselves to an isomorphism of coordinate ring. So we have from birational equivalence, we get to an isomorphism equivalence.
Yes, that's true.
No, This is somehow contradictory.
How?
I am saying from this isomorphism of field, I can get an isomorphism between coordinate ring.
Oh, sorry. No, that's not true. That's not true.
Oh.
Definitely, if that will be true, then definitely you
Yes.
will have the birational one. I'm sorry. No. It's not. If you will restrict on the corresponding coordinate rings, then definitely you don't have any isomorphism.
It's not isomorphism.
Yeah, sorry about that. Okay, if anyone has, there is some question, I think, if you will say that, yeah. Is birational if there is a rational map which is its inverse? Yeah, I said that. What does it mean that phi is birational map? If there is another map which is called psi, you can say the psi, which is again a rational map, and they are inverses to each other. So then definitely this is called birational map. Like as I said before, for isomorphism, whenever you have the inverse map, it must satisfy the regular condition. The same is true for the birational equivalent. If you have phi is birational equivalent, then this means that its inverse map is also a rational map. Okay? Can you see more? Okay. Birational map is actually like it's if you will say that it's playing a role like an isomorphism in some setting. So definitely it is an equivalence relation. If you have a birational map, every variety is birationally equivalent to itself. If you have if something is birational to other one, definitely the other one is birational to itself. To the same one, and that definitely there is a transitivity one, so that's why the answer is yes. Birational map is an equivalence relation. Okay, is there any other question?